this very kind introduction and also your invitation to present my work here. As you said, I'm going to talk about the topic in population genetics. And in population genetics, we try to understand how forces such as selection, mutation, recombination, inheritance, migration, and others affect the genetic composition of populations. It is how they drive their evolution. And one of the prime topics is the study of adaptation to a changing or also to a new environment, and which factors facilitate, retard, or even hinder that. And today I will talk about work with my former PhD student Martin Pons on certain aspects of adaptation in a heterogeneous environment and in a structured population. This work is a part of his thesis, which he defended successfully in spring, and it was motivated by previous work that I had performed in collaboration with a former postdoc of mine, Simon Eschbacher, and also with Sam Yeaman from the University of Calgary. So, as we know, many species live in a structured or in a heterogeneous habitat. And adaptation is crucial for long-term survival because in such a structured habitat, in different patches, different environmental conditions occur, and they may change in time. In order that local adaptation can occur, one needs, for instance, mutations that occur and that are beneficial in the focal environment. However, they could be deleterious elsewhere. So we do not consider here mutations that are unconditionally beneficial. And it also requires that these mutations do not only occur, pop up and then disappear, but they need to become established, by which I mean they reach sufficiently high frequency so that they can reach a stable polymorphic equilibrium or maybe even go to fixation. And such spatially heterogeneous selection and concomitant local adaptation may lead to population divergence, divergence among subpopulations, and in the very long run, also to speciation. However, there are always limits to local adaptation. And in a spatially structured population with migration, one of these important limits is maladaptive gene flow, which may be caused by immigration of poorly adapted individuals into the new habitat, where already some well-adapted individuals are living and using that habitat. Especially then if there's competition between these types, as it will be if the resources are limited. And of course, there are plenty of stochastic effects. New mutants are rare, thus they may be lost by random factors, especially by random genetic drift. And of course, also the availability of appropriate mutations is a topic, but that's beyond the theoretical aspects we are going to talk about today. There are a number of empirical insights already on local adaptation in the presence of gene flow. And there are several studies who found that there are quite extended regions in the genome where there's elevated divergence between subpopulations. Mostly such divergence is measured by FSD-like statistics, which is based on heterozygosity measures within subpopulations and between subpopulations. And so what has been found is that in some species, clusters of loci occur where divergence is elevated, and they were called genomic islands of speciation, genomic islands of differentiation, or of divergence by different groups of authors. Here's one nice example of such a genomic island, or actually of two. That's from hybridizing butterfly species, where the divergence, you see it measured on the on the vertical axis by FST, is elevated above average, statistically significantly elevated in these gray regions. This is one cluster in one part of the genome, and here is another cluster in another part of the genome. And essentially, this divergence is mainly concentrated in these regions. There are, of course, studies of other species who found no such clusters, but instead found that these regions of elevated divergence are distributed more or less randomly across the whole genome. So it is a phenomenon that does, of course, not always occur. And the question is, the first question from the biological point of view, what can be learned about the evolutionary history of a species by studying such genomic islands? And in order to be able to make inferences, we actually have to understand when and under which conditions we expect them to arise. And this is essentially the topic of my presentation here. So I start with the simplest spatial model that one can imagine. It's a so-called continent island model. And in this continent island, in this continent island model, there's a so-called island population, or it could also be a peripheral population, which receives immigrants from the so-called continental or mainland population. And this mainland or continental population is assumed to be well adapted, but individuals leave to explore their environment and may, for instance, inhabit a different patch or an island. On this island, selection favors different phenotypes or genotypes than on the continent. And also back migration to the continent is ignored, either because it does not occur or because of low numbers and the excellent adaptation on the continent. It has no effect. And there's actually one beautiful empirical example of that. These are water snakes in Lake Erie, a system that has been studied for more than 100 years. And there, the continent is actually the mainland around the lake. Okay, so how do we model selection on the island? We shall assume, and you will see soon why, that we have selection on two loci, A and B. At each of these loci, two alleles can occur, and these loci occur at a certain recombinational distance. If R, the recombination frequency, is small, this means that they sit close together on the same chromosome. If R is large, the largest value is 1/2, then they sit either on different arms of the same chromosome or even on different chromosomes. And in this biological scenario, we assume that on the continent, what we call the wild type A2, B2 is fixed and does well there. On the island, there's at the B locus already an allele, a mutant B1 has occurred that has a substantial selective advantage over B2. And this advantage is sufficiently large so that it could reach migration selection balance despite the immigration of individuals from the continent. And this requires essentially, we will see this on one of the next slides, the selective advantage of B1 exceeds the immigration rate M. And so this is our starting point. We already have a fixed polymorphism on the island, which exists because one sufficiently favorable mutant occurred that made it to fixation that made it to establishment. And the idea behind this is that subsequently at other loci also beneficial mutants can occur, but it is well known that, that strongly beneficial mutations are much, much rarer than weakly beneficial mutations. So the question is, can very weakly beneficial mutations become established if there is already a polymorphism? Because weakly beneficial mutations could not be established in the first step because their selective advantage is too small and they would be swamped by immigrants from the island. So this mutation A1, which we're interested in, it can occur either on the background B1 with probability Q, if Q is the frequency of B1 at this polymorphism, or it occurs at the other background B2, which is the continental background essentially, which happens with probability 1 of minus Q. And then we ask, under which condition can such an allele invade or become extinct? And if it invades, what is the invasion probability? And our goal here is to study the fate of such a single new mutant, which in general will have a small effect. And we study only the island because what's going on the island does not affect the continent, the continental population. So in this simplified model here, we just assume a haploid population, which is essentially equivalent to a diploid without dominance. We have discrete generations. I already said that the fitness of B1 is higher than the fitness of B2, and we call this selective advantage B. And then in a deterministic model of an infinite population, there's a globally asymptotically stable migration selection equilibrium if and only if the migration rate is lower than a critical value, and this critical value is essentially B unless B is large. But if B is small, then this of course is close to B, and this is a result that goes back to Haldane almost 100 years ago. And of course then there's an equilibrium frequency which is easy to calculate, and this equilibrium frequency of B1 is close to 1 if M is much smaller than B, so if the selective advantage is large, but this equilibrium frequency can be fairly small if M is not much smaller than B. Okay, so this is the starting point. And now let's look at a stochastic simulation, actually of a White-Fisher model in a finite population. I think there were 1,000 individuals, and the initial situation was that at the B locus the B locus was in equilibrium. I mean, here in a stochastic equilibrium, so frequencies here close to 0.5 for these parameters. And then a new mutant A1 occurs. The frequency of the mutant on the vertical axis is black dots. And the mutant can in principle occur on this background or on the other background. If it occurs on the B1, on the favorable background, it's blue. The color is blue, and the frequency of these gametes here is in red. And here actually you won't be able to see it, but we will see it immediately. The allele A1 occurred on the poor background here as this type of gamete. But eventually by recombination, it made it on the other background, and then it spread in frequency, and migration selection equilibrium is reached. I mean, stochastic stochastic equilibrium, or quasi-stochastic actually in that case. So let's briefly zoom in what's going on in this initial phase here in the first generations. Yeah. So the mutant in its frequency here is the frequency of the mutant are black dots, the frequency of the gamete A1, B2 are these red circles, and the frequency of the other gamete are the blue circles. So it occurred in a single copy on the bad background. For two generations, for one generation, it spread, sorry. Sorry. And then a recombination event occurred here, because here the frequency of the mutant is just the sum of the frequency of the two gametes. And here one copy made it into the other gamete by a recombination event. Then there's some fluctuation, but the mutant remained in the favorable, on the favorable background. Here only is a single copy. There's further fluctuation. The red gamete has already been lost because it has a lower fitness. And once it has reached a certain frequency, then it thrives. And then you can see once it has reached a critical frequency, it behaves almost deterministically and spreads through the population. Of course, by rare recombinational event, it also comes back into the red background again. Okay, so this is what can happen because of recombination. And for those who are not that firm, in population genetics, I want to very briefly explain the ambiguous role that recombination can have. So with recombination, mutants that arise in different backgrounds, so the strings here are gametes or individuals, if you want, and there are one locus and here's another locus. Yeah? And so the red here are beneficial mutants on this locus, the red here in the squares are beneficial mutants on the other locus. So typically a mutant, yeah, it may occur on one or the other gamete. If we have this situation, then if a recombination event occurs, then the two mutants together have a higher fitness than each of the other strains, and the probability of becoming established will be elevated. So that's the favorable role that recombination can play. However, it can also play a negative role, because if initially we have two favorable mutants in the same individual, then recombination may break up this optimal haplotype. And of course, this also occurs if there are already many such haplotypes. And then they will be separated, and the optimal haplotype may actually be lost, at least for some time. And then, of course, adaptation will be slowed down, because there will actually be competition between these two types. And this ambiguous role of recombination is one of the reasons why already long ago some authors suggested that clustering of locally beneficial mutations should occur. And of course, they supported their these assertions by computer simulations. Okay, so here we will also do simulations, but we are mainly interested in deterministic models, in mathematical modeling, sorry. And what we do is we model the initial invasion process by a Golden-Watson process, by a two-type Golden-Watson process. So we assume essentially that the mutant arises in an infinitely large population or in an extremely large population. And then we just look at the stochasticity that occurs in the initial phase when the mutant is rare. So what we have, this mutant A1 arises either in this gamete, A1, B1, or in the other gamete. Yeah, we already had this. Here's a summary again of the fitnesses. A2, B2 is the wild type. It has a relative fitness of 1. On the back, the B1 has an advantage. Its fitness is 1 plus B. And now the favorable mutant on the island, the A1, has already on the poorer background an advantage A, yeah, and on the on B1 it may have a different advantage, A plus E, and A is called the additive fitness effect, and E is called the epistatic effect, and this can be positive or negative. And throughout, we always assume that A is less than B, because otherwise we already know by assumptions of the model that the mutant A1 could invade whether it is linked or not. And so we focus on new mutants of small effect compared to the already established mutant. So what we need to do is we need to study the invasion process. And in principle, two mutant types can occur and will occur by recombination, A1B1 and A1B2. And we assume that each of these types reproduces independently, and the offspring distribution is Poisson, and the mean of the offspring distribution is given by the fitnesses I showed before. So what we need to do is we need to linearize the dynamics of the frequencies x1 of A1B1 and x2 of A1B2 near the boundary equilibrium, which is formed by the resident types. And this linear dynamics looks like this. And here M is the matrix that gives the expected number of J-type offspring of an I-type individual. So here, this entry here is the expected number of offspring of type 1 by a parent of type 1. And this here is the expected number of offspring of type 2 by a parent of type 1. And you see that these offspring here are only produced in proportion to the recombination rate, yeah, which is kind of obvious. Okay, so then it is well known from branching process theory that invasion can occur if and only if the leading eigenvalue of this matrix is positive. This leading eigenvalue can be computed explicitly, but it gives a fairly complicated quadratic equation. Nevertheless, we get relatively simple invasion conditions. For this purpose, we have to define two critical values. One is denoted by E sub r, and it will play a role for the epistasis. You don't need to recall the precise values, but this E sub r can be negative or positive. Yeah? And the other one, the M star, has to do with the critical migration rate, as we shall see. It is even more complicated, and it has the property that this eigenvalue lambda equals 1 if and only if the migration rate assumes this value M star. Yeah? And now we are able to formulate the invasion conditions. Again, we recall that M sub B is the maximum migration range for which our polymorphism at locus B exists, and our model is only defined and studied for the case where such a polymorphism indeed exists. So the migration rate needs to be between 0 and this bound here. Otherwise, we are not interested in it, because then, yeah. Okay, then we obtain 3 mutually exclusive conditions which cover the complete parameter range. The first says that if E is smaller than negative A, then there's no invasion. What does this mean? In this case, we actually have that the fitness of the best type, well, of A1, B1, which should be the best type, is lower than the fitness of the essentially original type. There's sign epistasis, and so actually epistasis reverses an advantage in a disadvantage, so there cannot be any invasion. If E is larger than the negative of the additive effect, so that in summary there's a positive effect, but lower than this critical value ER, which still may be negative or positive, that depends on the parameters. Then this critical migration rate M star is larger than 0 and smaller than our maximum migration rate for which the model, as it is formulated, makes sense. And then invasion can occur for all migration rates that are smaller than this critical value, yeah, but not up to the maximum of MB. And the third case, if epistasis is sufficiently strong, not necessarily positive, but if it is strongly positive, then usually this will hold, then invasion of the new mutant is possible for all admissible migration rates. Yeah. So we know when invasion can occur. But of course, in a stochastic model and in a branching process, we know that even if invasion is possible, it does not occur with probability 1. Actually, it may be very small. And one knows from the stochastic version of the continent island model, and that's all. Essentially, that goes back to work by Fischer and Haldane, that the invasion probability is on the order of S or even S minus M if there is migration in a finite population. So we want to study the invasion probabilities. And pi1 is the invasion probability of A1 if it occurs on the good background, and pi2 is the invasion probability if it occurs on the bad background. And it is known from theory that this pair of invasion probabilities can be obtained from the non-trivial fixed point of the generating function of the offspring produced. And we have a Poisson offspring distribution, so we obtain a system of transcendental equations which cannot be solved analytically, but which is easy to solve numerically, of course. And of particular interest is, of course, for us the unconditional invasion probability or the averaged invasion probability, because we do not know a priori on which background the allele may occur. So we need actually the weighted probability between pi1 and pi2. So how can we proceed? We're interested only in mutations that have an advantage, which means that we are interested essentially in the supercritical case. And for the slightly supercritical case, which I write a little bit sloppily here, that lambda is 1 plus epsilon. The epsilon means it is actually a small function of some parameter epsilon, a function of some small parameter epsilon, but lambda is just a little bit larger than 1. For this slightly supercritical case, Thrier derived an approximation for the invasion probabilities of a multi-type process. And for a much nicer representation of the results, have a look at the book by Hakau, Jagas and Vatutin. And in our two-type process, these two invasion probabilities can be written in this form. Of course, the leading eigenvalue comes in. It has to be reduced by 1. So you see, this is 0 exactly if lambda equals 1. The components of the left eigenvector come in, and the complicated term beta, which for independent Poisson distributions is given by this expression here. And the UJs are the components of the right eigenvector. We do not need the explicit formulas. Explicit formulas can be computed of these expressions using Mathematica. They are extremely complicated, but easy to evaluate numerically. So before we will see simple approximations a little bit later. So let's first have a look of comparing the true and the approximate invasion probabilities. By true, I always mean the numerically exact solution. And here we see this averaged or unconditional invasion probability as a function of the migration rate. What we see is for all parameters in all cases, this is always a strictly decreasing function in M, and this can actually be shown. Yeah, so A and B here are specific parameters. A is smaller than B, yeah, and here the recombination rate here is fixed to 0.1. What we also see is by the color coding that black is no epistasis, with positive epistasis, invasion probability is elevated, with negative epistasis, it is reduced, but is actually what would be also expected intuitively. The solid lines are of the exact numerical solution. The short dashed line, which is always below the solid line, is the approximation that Martin and I derived from the Arthria approximation. And the other dashed approximation is one that Simon Eschbacher and I derived also from the Arthria approximation, but with a trivial computational error. We lost a square at some place. So why do I show this wrong approximation? Yeah, so let's first look at this slide here. Same parameters A and B, but now we show the invasion probability as a function of the recombination rate, but now for a fixed migration rate. And again, we see epistasis always increases invasion probability, that's clear. But for this parameter combination, the interesting thing is that the true approximation is no longer maximized at the recombination rate of 0. It is maximized at a small but positive recombination rate. Also here, but here it's not visible because the optimum is at 0.001 or something like that. However, the correct, in the sense of Arthria, correct approximation is the short dashed one. It does not show this maximum. For magical reasons, the approximation that I derived is Eschbacher usually produces this maximum quite correctly. And in fact, from this approximation with Simon Eschbacher, one gets a nice and very accurate bound on the parameter range in which this maximum actually occurs, this positive optimal recombination rate. The A must be larger than B minus E over 2, and we have tested this for a large combination of the parameter range, and it turns out to be very accurate. From the Arthria approximation, from the correctly evaluated, one obtains just that A is greater or equal than B, and only second order terms then are negative. So there essentially it never produces an optimal recombination rate. I do not know what the reason is. One of the reasons is that this usually applies if one is relatively far away from the supercritical case, from the critical case. So it's no longer slightly supercritical in a certain sense. Yeah. Anyway, so this is a mystery. I also mentioned we do have simple approximations. I don't have the time now to go into any detail, but for instance, if the mutational effects and the migration rates are small compared to the recombination rate and to the effect of the already established polymorphism, then again, both our correct approximation and the wrong one by Eschbacher and myself agree, yeah, to leading order. And then you obtain simple formulas from which you can easily explain the kind of behavior that we have seen before and that what one could see on other graphs. Among others, from this formula, one also gets an estimate of the maximum effect that epistasis can have in this case. And the maximum effect is 2e divided by 1 plus b. And again, magically, although this was derived for a limiting case, it seems to be a general upper bound for the increase of the invasion probability caused by epistasis. Okay, so let's come to something that brings us nearer to applications and to understand genomic islands. Clearly, efficient local adaptation will not only require successful invasion or establishment of 1 or 2 mutants, it will require establishment of several or even many weakly beneficial mutations. And in principle, they can occur at an arbitrary physical distance to the established polymorphism, also on other chromosomes. If there are many chromosomes, of course, they have a high probability to occur elsewhere. And also, neither their additive nor their epistatic fitness effects will be known a priori, and usually also not a posteriori, because they are difficult to measure. And for this reason, and the simple case was already initiated in the paper with Sam Yeeman a couple of years ago, we investigate scenarios in which the recombination rate between A and B is drawn from a uniform distribution. So essentially we measure distance in Morgans, and also the effects, fitness effects A and E of the mutants are drawn from, this case, empirically motivated distributions. So as we say, we draw the recombination rate from a uniform distribution. The additive effects are drawn from an exponential distribution with a given mean, which we denote by A bar. And there exists studies that support that. Actually, this is a study where it's shown that additive advantageous effects following exponential distribution. For epistatic effects, we assume 2 distributions, each received support. One is between mutations of arbitrary effect, actually derived from Fisher's geometric model and comparing with data from microorganisms and bacteria and others. In this first distribution, it's just a normal distribution with 0 mean, but a certain variance. Yeah, and the other, which is a distribution that has been derived from measured interaction effects among beneficial mutations. This is a normal distribution again, but with a negative mean and a certain variance. Yeah. So this actually was derived from interactions among beneficial mutations. And here, only 10% of all mutations here are beneficial. Yeah, but the distribution has a relatively large variance. So let's look on what do these distributions do now. And of course, if I show invasion probability here, this is now the invasion probability. It's unconditional and it's averaged over the distributions, over the corresponding distributions. The black curves are for the case where there's no epistasis at all. Yeah, so that's similar to what we had previously, but the additive effects are drawn from an exponential distribution, and the dashing here. Okay, maybe let's first consider the colors. Again, as we see before, if effects are on average negative, then of course invasion probability is reduced, here orange. If effects are on average 0, but are drawn from a normal distribution, then there's a significant elevation of the invasion probability compared to the corresponding curves of which are black and where there's no epistasis. And what we also see is the dashing here shows linkage. The long dashing is just free recombination. The solid line is recombination drawn from an uniform distribution at 0, 1/2, and the short dashed line is for tight linkage. So tight linkage in all cases elevates invasion probability, and also if recombination rates are drawn from a if they are drawn from a distribution, that's still better than having a recombination rate here of a higher than 0.5. There's another more interesting aspect which goes beyond what we have already seen before. What you see here is, for instance, here, but also down there, that curves of different color and dashing style can cross. Yeah, so here, for instance, the short dashed line is the short dashed black curve is above the solid green if M is large, but it is below if M is small. And what does this mean? This means as long as migration is small, weak, positive epistasis, higher fitness advantage, provides the greater advantage than tight linkage to the already existing polymorphism, whereas for large M, tight linkage is much better than more positive epistasis. Yeah. So whether epistasis or linkage favors invasion actually depends on the migration rate, whether it is low or whether it is high. And this brings us to our last topic. I mean, I started with these genomic islands or clusters of divergence. And just to recall, these are clusters of sites that contribute to divergence, typically measured by FST. And following the previous paper by Yeaman and Simon Eschbacher, we define a window size Cn as the smallest neighborhood of the already polymorphic site in which n% of all new mutations become established. So what does this mean? A small window size means that most mutations occur in a locally restricted genomic mutation region in the neighborhood of the already polymorphic site. A large window size means that essentially there is no cluster and linkage is of little relevance. Yeah. Okay, so let's look at such sizes. Here I show C50, we could also show C90, whatever. And here I first show it for the simple case where all effects are fixed, because then it's easier to understand what's going on. The first thing is, so on the vertical axis, we see the window size. On the horizontal axis, the migration rate. And clearly, the window size decreases sharply, essentially from its maximum possible value of 25 Morgans here to a small value and close to 0 for high migration rates. And this decline strongly depends on the strength of the additive effects, and it also depends on the epistatic effects. So the additive effects, here's a small additive effect of 0.01, 0.03, 0.05. The larger the additive effect, the wider is the window, for the obvious reason, because even if the migration rate is relatively large, if mutants have large effect, they have a high probability of invasion. Mutants of small effect have a low probability of invasion if migration is strong. And also epistasis has the effect that we expect from before. Negative epistasis is the short dashed line. It's always below the case of no epistasis at all. And positive epistasis increases window size because it makes invasion easier. Yeah? And now let's look what's happened if we draw, for instance, if we draw the additive effects from a distribution, from an exponential distribution. Then we obtain the black curves. What you see is, of course, it also declines with the migration rate, but the decline is much more shallow and gradual. If here the effect is drawn from an exponential distribution with the mean of 0.01. Yeah, the mean is the same as for the red line, for the red curves here. So for very small migration rates, it doesn't make a difference. If it's an exponential distribution, of course, mutations of small effect occur frequently, mutations of large effect occur rarely, but they do occur. But the larger the migration rate, the more, the larger the migration rate, the lower becomes this window, or the smaller becomes this window here, compared, for instance, to this. And compared to this, it becomes larger. Why? Because with the higher migration rate, the invasion probability of mutants of large effect increases. Those of small effects goes down rapidly. And all this is conditioned on successful invasion. So what you see is only the successful mutants. And this explains why for large M, actually here, the window size is substantially elevated over the case where we have a fixed mutational, a fixed fitness effect. So, a very brief slide, because I'm already close to the end. Of course, we can study the effects of those mutations that are successful, yeah, because that's what determines these windows. And if the migration rate is low, the average effects of the successful mutations is here. In one case, it's drawn. In one case, the epistatic effect is drawn from the normal distribution with mean 0. In the other, from the one with negative mean. But in all cases, the effects are much larger than the mean, which would be 0.01. And with small migration rates, the effects of mutations that become established are extremely high, but of course they will have a very low probability of actually occurring. And if they occur, then of course they have a high chance of becoming established. So this also explains these shapes of window sizes. There's one interesting aspect. If epistatic effects are drawn from the distribution with negative mean, then the additive effects are elevated, because there's always a balance between these additive and elevated and epistatic effects. If mainly, if most epistatic effects are negative, then in fact the additive effect has to be sufficiently high in order to accommodate this missing contribution from positive epistasis. Okay, so a last slide actually here is now we draw everything from distributions except the black line. So here just the additive effect is drawn from the exponential distribution, and there's no epistasis. And now we draw epistatic effects either from, in the green case, from the distribution with 0 mean, or here from the distribution with negative mean. And the surprising thing is that even negative epistasis increases the window size, just very little, of course. There's no big effect. but the effect is clearly visible. And the reason is that with if additive effects are predominantly negative, then only those mutations can invade that have a correspondingly stronger positive additive effect, and the additive effect is actually the more important one. And with a strong positive effect, you do not need as much linkage as with a small additive effect. Therefore, the window size increases. Yeah? And of course, if one considers a fixed epistatic effect, then the window size always increases, because this is always of an advantage for elevated invasion probability of a mutant if the total effect is substantially increased. Okay, I think I'm at the end of my time. An interesting question in this connection is, of course, the time frame in which such clusters can emerge, because mutants of small effect, for instance, they occur frequently, but they are difficult to detect. So it may be that they cannot be even detected, and such a cluster would not be found. On the other hand, mutants of large effect are rare, but then they have a relatively high invasion probability. So there may actually be a bias in detecting such clusters, just because of the limits of inference. And again, I would like to thank my previous co-author and my current co-author, Martin Pons, and also some financial support by the Austrian Science Fund, which supported both Simon and Martin. Thank you very much for your attention.